of A star times determinant of A, and determinant of A star is 1 over determinant of A multiplied by determinant of A, which is equal to 1. So this means that we can put the value of A star. A star is the of A, and transpose will not change the determinant, so we can write this as determinant of the conjugate of A. This will be equal to 1, that we have just seen here. This means that determinant of A square is equal to 1, and from here we can say that determinant of A is equal to plus minus 1. So we can conclude that the determinant of a unitary matrix has absolute value 1, that is, it can be plus 1 or minus 1.
Sir, how do you say that determinant of A conjugate is equal to determinant of A?
Yes, sir.
Sorry?
How did you declare that determinant of A conjugate is equal to determinant of A?
Determinant of A conjugate. You can check this. You can take any simple matrix 2 by 2, and then you can verify this, and then you can generalize this for matrix of any order.
Okay.
Okay. So this completes this section. And some examples are there for example, we have an example of Hermitian matrix. We have an example of unitary matrix, normal matrix, and skew Hermitian matrix. So you can verify the conditions of the Hermitian, skew Hermitian, normal matrix, unitary matrix for these matrices, and you can see that the conditions are satisfied. So these are some examples. Now let us move to the next topic, eigenvalue and eigenvectors. So for eigenvalue, you can for eigenvalue, let us for this section, let us consider a system of equation Ax is equal to lambda x, where lambda is some real number. Now from this equation, one can clearly see that if I take x is equal to 0, then 0 is the trivial solution of this equation. So remember that everything is written in the matrix notation. I think this should be bold x. This should be bold x. So you have a matrix A which is of order n cross n. You have a vector x which is of order n cross 1. Then a real number lambda, that means 1 cross 1, and x is n cross 1. So everything is in matrix notation. And when I say that x is equal to 0 is the solution, that means the vector 0, which consists of all the components as 0, this is the solution of this equation, always. Okay. In the eigenvalue problem, we are interested in finding the value of lambda for which the system has a non-zero solution. That means you can that means you have to find a value of lambda so that you have a solution which is not equal to 0. You have a solution of this system of equation which is not equal to 0. These values of lambda is known as eigenvalues of the matrix A. And the corresponding vectors or the corresponding solution that you obtain is known as the eigenvectors of A. Okay, so first you identify a value of lambda so that you can identify a non-trivial solution of the system AX is equal to lambda x. This lambda, the lambda that you have obtained, is known as the eigenvalue, and the solution that you obtain, which is the non-zero solution or the non-trivial solution, is known as the eigenvectors of A. Now this will, so the purpose is to identify a non-zero solution. So we can first of all write this equation in this form. Now this is a system of homogeneous equation. This is a system of homogeneous equation. The system of homogeneous equation will have a non-trivial solution only if the determinant of A minus lambda I is 0. Okay. So this is the third point here. The above system has non-zero solution if and only if the determinant of A minus lambda I is 0. If A minus lambda I has non-zero determinant, that means A minus lambda I is non-singular, then trivial solution x is equal to 0 is the only solution of this system, the only unique solution of this system. Okay, so for this system to have a non-zero solution other than the trivial solution, that means the solution other than the trivial solution, the determinant of A minus lambda I must be 0. Okay, and this gives us an equation. This gives us a polynomial in lambda. This equation is known as the characteristic equation of A, of the matrix A. And the polynomial A minus lambda I is known as the characteristic polynomial